We've finally built up enough machinery to be able to actually study orbits using the gravitational potential. We are interested in what are the shapes of orbits that planets can orbit the sun with. There's a circle, there's ellipse, and as we'll see, there's also the parabola and the hyperbola. And we'll get that out of the effective potential that we've derived and the inequality, the energy inequality that we need. So the concept is to sketch, or the objective here is to sketch U effective for the gravitational potential. So U effective we got in concept 8.5. It is a function of r only and involves the angular momentum L, which is a constant, it's conserved, divided by 2 times the mass of the orbiting object, the distance from the sun to the planet which is orbiting, plus a general potential, r-dependent potential U of r. We're going to specialize to the gravitational potential, which does depend on r, but in this particular way. It's a -1 over r potential. We derive that in concept 8.3. This is a fun one because it brings together so many different concepts. And then finally, the last concept that we did, 8.6, we showed this energy inequality, and that will be crucial in our understanding of the basic properties of these various orbits. So the first thing I'd like to do is to insert this gravitational potential into here. And this is what we'll be working with. Let's sketch U effective of r. Now, that's our next goal. Let's see if I can do it like this. There's r. Here's U effective. Well, what does it do? Let's look first as r goes to 0. As I'm going to factor out a 1 over r, that will help us determine what this thing is going to look like. So I'm factoring out a 1 over r from both terms. This term will give me L squared over 2mr. And this term, when I factor out the 1 over r, will just give me gmm. So now, it's easier to compare what's going to happen as in the various limits of r going to 0 and r going to infinity. As r goes to 0, this term is constant, so it's just a constant. But as r goes to 0, this denominator gets huge. And so this fraction gets small, because 1 over a large denominator gives a small number. And so that term is going to dominate as r goes to 0. This is just constant. This one will go to infinity. So U effective as r goes to 0, U effective is dominated by this term. All right, so what does that mean in terms of plotting U effective as a function of r? Well, what does this function look like? As r goes to 0, again, we have a big number in the denominator. And this U effective is going to go to infinity. There's no minus sign out in front of this, so that means that U effective is going to go to a positive infinity. So this is L squared over 2mr squared. And that's what happens as r goes to 0. What about as r goes to infinity? As I've talked about before, the ability to plot out a function just by taking limits and looking at the maximum minima as needed is very, very important. All right, so what about r goes to infinity? Well, as r goes to infinity, this term, the r is going to infinity, and we have 1 over infinity, that's 0. This one approaches 0. So the u effective is going to be dominated by this term as r goes to infinity, because any constant is going to be bigger than something that's going to 0. So it just goes like minus g m over r. So it's like the second term. Well, what does that look like on this plot? First of all, it's negative. Second of all, as r goes to infinity, this denominator is going to infinity, and 1 over infinity goes to 0. So it's going to be negative, and it approaches 0 as r goes to infinity. So it's going to look something like this as r goes to infinity. So what does it do in between? Well, good question. First of all, to get from here to here, we know it has to cross the axis, and we don't have any singularities in this at finite values of r. So what it's going to have to do is something like that. In fact, it does reach a minimum, which you can find, and which I'll ask you to do as one of the homework problems. So that's u effective of r. We've done the first part, and we're going to use now the energy inequality to identify the basic properties of circular, elliptical, parabolic, and hyperbolic orbits. This part is just truly fun, because here u effective is 0, here u effective is positive, here u effective is negative, and we're going to ask about the energy level now. So now we're going to focus on this this inequality. E minus u effective has to be greater than or equal to 0. What does that say about E? Well, if you add u effective to both sides of the equation, that says that E has to be greater than u effective. So what if we choose an energy value that's lower than this minimum? You might say, well, everywhere along here, E is less than u effective. And so this is not possible. And just as a reminder of why it's impossible, it's that would mean that if E is less than u effective, this number would be negative, but that number can't be negative because it has to be positive definite. So that's an impossible orbit. What's the smallest value of E for which we can get a legal orbit? Well, you might say, what about this one? At that value of E, where it exactly touches the bottom of that minimum, we have one spot on this curve that's permissible, and that is a circular orbit. How do I know? Well, if I label this energy and the radius that's associated with it as E naught and R naught, then what we're seeing by this is that there's only one energy that satisfies this relationship, and it is that energy E naught, and that happens to occur for the value of R naught. So E equals U effective of R naught. So E naught is U effective of R naught. And how do you find that R naught? Well, you'll do it as a homework problem, and you'll find the minimum. Just take the derivative of U effective with respect to R, and you'll find that minimum. That's a circular orbit. How do I know it's circular? It's because that R is always equal to R naught. There's no other value that R can be. And so if we're thinking about polar coordinates, then and here's where the mass is, and here's where the central mass is. So this is the planet, this is the sun. R is equal to a constant no matter what phi is. So R is going to be equal to a constant. That means that thing is going to be going around in a circle. As easy as that. All right, let's take a look at another value. Let's look at this one. Let me call that E sub E because it's going to turn out to be an elliptical orbit. That's an energy for an elliptical orbit. Now, which values of R, for which values of R is this inequality satisfied? Well, E has to be greater than or equal to U effective. Here, E is less than U effective. You can see U effective is higher than E is here. But here, inside this region, E is constant, remember. Angular momentum and the energy are both constants of the motion. So in here, the energy is greater than U effective because it's higher than it in the graph. So I'm going to actually darken in this to say that those values of R between some minimum and some maximum are allowed. I'm going to call this R min and this R max. So the dotted lines, just for your reference, means not allowed. So what we're seeing for this particular value of E, a value between here and here, we get two places where, well, we get R in a range. So this inequality allows for a range of R between R min and R max. That's an elliptical orbit. And how can you imagine it over here? Well, that will mean that it'll be going along for a while with R decreasing down to a minimum, then it'll be going along for a while with R increasing up to a maximum, and we get an orbit that looks like this, where this distance here is R max, and this distance here from the origin out to this point here is R min. So it's going to orbit around with the sun. As we'll show later, we haven't actually proved it's an ellipse yet. We will in the next concept or two. But you can get the basic idea that it's going to be going between some maximum value and some minimum value, and that looks to be something like an ellipse. It's still a bound orbit, meaning it's not going off to infinity. It's staying in the general vicinity of the sun. All right, so what about this one? I'm going to call that EP because it's going to coincide with a parabolic orbit. How do you know that? Well, this is our axis, but this part really should be, let's actually replace it with a dotted line, because it's not allowed. Its energy is less than the effective potential. But here, all these orbits, all the way out to infinity, are allowed. This minimum, for this particular case, comes all the way down to here. So what we're talking about is an orbit whose maximum R value goes off to infinity, but its minimum is still finite. And so this over here, and we get a parabolic orbit. So what does it look like? Something like that. So instead of closing back in on itself like this elliptical orbit did, it's going to keep on growing out to infinity. And then finally, for EH, which will turn out to be a hyperbolic orbit, this is not allowed and this is allowed. So that looks very similar to the parabolic orbit. It has a minimum and no maximum. And so this is so we can't see from this basic analysis of the graph, we can't tell the difference between a parabola and a hyperbola. But we can see that the parabola is right on the boundary between being bound and unbound. The parabola and the parabolic and the hyperbolic orbits are both unbound. They do not remain in the vicinity of the sun. They head off to infinity, but the bound orbits look like this. So comets, some comets are in unbound orbits, and then they get kicked and their orbits become elliptical. Well, actually, the more common scenario is that they're in some kind of a bound orbit, an elliptical orbit, then they get kicked when they come too close to a planet and get kicked into an unbound orbit, and they head off to infinity and you never see them again. But it's just amazing how much physics you can get out of this effective potential. And this helps to justify all the mathematical work that we've done so far in trying to understand this problem.